All right, thank you, Peter, and thank you all. It's tough to follow Michael Stein, but I'll give it a shot. At least Michael said in his webinar that it's okay for us to pontificate a little bit. So I'll do the same, following his lead. Not too much, but a bit. So here's a quick outline. I guess the main thing I want to talk about is model error and a variety of ways of dealing with that model error. And in doing so, sort of separate into two basic strategies. One where the model is manageable enough that you can actually start modeling the model error and put it into the model in some sense, into your statistical model. And the other is at massive scales. Like I'm not going to put a model for my numerical model error into a climate system model. So what can we do in that context to still manage something about error? And I'll primarily do some examples, but I want to first talk about a little bit about the whole issue. So we're all pretty familiar with lots and lots of sources of error. Of course, there's this notion that anything that we implement or write down is an approximation to what nature can do. Surely we always tend to, for practical reasons, leave out some effects that we may or may not think are relevant. We might leave them out just because they're too hard to put in. That's not a very good reason. The other reason is maybe we think they're not very important, but maybe they are. Parameterizations, that's kind of a numerical modeling issue, and if you don't know what I mean by parameterizations, that's okay. But surely everybody knows about numerical error in large codes. There can be coding errors, but also there's all sorts of issues about round off. A lot of what goes on in day-to-day is approximating a continuous system by a discretized system, so that induces some uncertainty or error, if you like. So there's a lot. There's a ... there, and you can fill in your favorite. Being a good statistician, being a statistician, to me, in trying to understand and deal with model error, the observations are critical. There's a notion that I'm going to sort of assume, and that is that the observations are really the truth plus noise. If I'm in a setting where I don't know that there's more model error in the model versus more model error in the observations, then I have a little bit of trouble. But I'm going to assume that the observations are a bit reliable, in the sense unbiased. They're useful in assessing and moderating the impact of error. We all know about calibration, and surely they're valuable in a variety of contexts of inferences that we might be after. Okay, so as I said above, you can see what I'm going to mean by a statistical model error. Whoop. I'm a kind of a PDF retard here, apparently. Why is it doing that? All right, well, you can't see my little hand, but pretend that green arrow up there is pointing down to the first equation. I'm going to use Y to denote data. It's indexed both by spatial locations and by time. And I'm thinking about Y as an observation. The real process of interest, however, is X. And I'm imagining that my observations are X plus some unbiased or mean zero measurement error. Okay? So in general, in terms of writing out probability theory, you might think of this as the conditional distribution. This is the conditional distribution of Y given the truth, X. Okay? And maybe we assume that it's Gaussian with some kind of variance, but of course those are examples. But the key to emphasize, although it's not always reflected in notation, when people write down equations like this, they're specifying a conditional distribution. At least I hope they are. So let's start with small to moderate scales and see what I mean by trying to do something here. So here's some highfalutin notation that's not very implementable, but it kind of gives a framework for what we want to think about. Imagine that nature is implementing a process model, that is, it's determining how X evolves in space and time, by implementing some equations. The equations are denoted by capital G, that's the nature's model. It's specifying something about the truth, and that truth depends upon cap F, which is maybe some external forcings. If you like climate, think about solar and human influences and all that sort of thing. And typically there's a collection of parameters as well, say cap theta. So nature is running that gigantic model and producing X for us. We can only approximate that by a lowercase model, lowercase g. I've written down something fairly similar, but I'm now denoting X with a tilde on top of it to remind myself that I'm thinking about I'm approximating X by X tilde. I'm approximating the true forcings, cap F, by some model I might have, little f. I'm approximating nature's parameters by a lowercase. I don't mean those are the same. And then finally notice that I've added a fourth variable there. And that fourth variable is the modeled error process that I'm going to induce. Okay? So again, I've tried to use notation that differentiates between things. I'm going to make a model for eta, but that model need not be the difference between nature and the truth. So I'm using epsilon there to remind myself consistently that epsilon is the difference between nature and my model. I'm hoping that I'm modeling epsilon pretty well by this eta thing, but I'm emphasizing that there's a difference between those two things. Okay. At massive scales, I'm not going to intentionally try and pretend that I'm going to put in a model for the model error directly into the system. So instead, I'm going to think about day-to-day operational things that we do typically. We don't usually analyze directly 10 million dimensional random vectors that are put out by a variety of models. Instead, what we usually do is define some summary or some dimension reduction of nature, of the true nature, and I'm going to use X to denote that summary from now on, okay? So X is no longer the entire continuous time-space planet. X is the variable or the summary of the climate system or whatever variable I'm studying, the summary that I've chosen to analyze. Again, X tilde now is not going to come from my model. Instead, I'm going to think of X tilde as being the corresponding summary from model output. Okay? So again, that output that you see, capital O up there, that's not me. That's NCAR or somebody else providing me with some output from a massive model that I don't even know how to run. And I'm just making a summary of that to look at and try and estimate X for them. From then on, everything almost looks similar. I'm going to use the same sort of observational data model. I'm going to think of my observations as being X, the true summarized variable that I'm studying, plus some measurement error. The computer model, this is kind of a slippery little step here. I'm actually going to think about the computer model and treat it as if it's observations. So I'm going to think of X tilde, my summary that comes from computer model, as being the truth. But now it's not just an unbiased estimate of the truth. Instead, we're going to put in some bias, B, okay? And that bias, B, is something that I have to deal with and model. I've also allowed for the opportunity to put in some extra error there by what is that, zeta? I don't know what that is. It's not zeta. That squiggly letter. And I'm putting that in to maybe allow for ensemble sampling from the same specifications. Maybe I get an ensemble from running the model at different initial conditions or different boundary values. But I'm still thinking it's basically trying to do the same structure. Okay. In this structure, remember that X now is a dimension reduced object that I'm looking at. So I can actually think about something besides the climate system model or the gigantic model that somebody's providing. I can actually put on a secondary model, a process model for X that comes from my beliefs about it. It might come from other models. It might come from other data, a variety of things. And I hope to clarify that with a quick example for a second. Okay, so emphasizing some notes here. Again, I'm not putting a model error into the numerical model. Instead, that step is being replaced by adding bias to the model output. Please note that there's no simple strategy here. If I choose to study a different summary variable, of course, then the bias and the ensembling variabilities change with the summary statistics. So if I'm doing one kind of summary, I have to restart almost if I take this strategy. And then, of course, we're going to need to model the bias in some sense and hopefully do a flexible model that we can learn about. Okay. A couple of brief notes and a couple of things to put a little perspective and just some discussion. Again, this is kind of a light presentation. I just wanted to put a couple of things in here that I think are relevant and interesting to compare to strategies that are more familiar or very familiar. Virtually everybody is very familiar with the Kennedy and O'Hagan strategy, and it's a wonderful paper and a wonderful idea. And here is a very brief, this doesn't do their work justice, but a very brief notion of what they sort of write down. So their data model is kind of similar to what I was writing down. Think about the conditional distribution of observations. These are real observations as being equal to X, which depends upon some fundamental parameters, and some other model outputs or control values C that I might have some control over. And then we always have some measurement error E. Then they write down this interesting expression, and I want to go back for a second. They write down that the truth, that is the true X, is equal to a data model, a computer model output X tilde plus delta, and delta is our famous discrepancy. And typically they might suggest a Gaussian random field. Now just 1 second. Let me go back as we discuss and compare that to what I wrote down as the computer model. The one way to think about this is to think about these kind of equalities as being specifications of conditional distributions, conditional distribution of the left-hand side given the right-hand side. Okay? So I'm thinking of the computer model output, the conditional distribution of that, if I actually knew the truth and the bias, would be following a model like that. Now, I don't know if Kennedy and O'Hagan would like me to do this, but I'm going to pretend that and do this. This is rather a strange notion if you adopt that view then. This is the conditional distribution of the truth given the computer model output has mean equal to the computer model output and then is screwed around by this discrepancy measure. I'm not sure they like that, but it really bothers me to see equalities written in statistics papers unless those equalities actually say something about a statistics model. And I'll show you what I mean by that in a second. Okay, so now what's the next step? If you accept that second equation, then you can simply substitute into the model, the data model, X equals X tilde plus the discrepancy, and now you get a nice model. The data model is equal to the data are equal to the computer model output plus the discrepancy plus measurement error. And if you do this, now you can structure, you have to put a model, of course, on the discrepancy, but you can now do some nice Bayesian inference. You can build a likelihood function and get some nice Bayesian inference for thetas, okay? You can play around with C, and you can do a lot of other things, too. In a sense, the reason I say that this is similar to approach 2 is I'm thinking about adding something like a bias although they call it a discrepancy or a bias to the model output, as opposed, again, to putting something into the model. There's some special issues here when you're doing this in the context of emulators for large models. And finally, the one note I wanted to make is that this separation into manageable small models and huge models that are unmanageable is a bit artificial. There's a whole spectrum of models that depend on your cleverness and your computational resources. And also to mention that dimension reduction can sort of serve as a bridge among those scales. So I don't want to think too rigidly a pigeonhole big models versus little models. Okay. So as I said, I really like to think about translate equalities into probability models. And so the outline that I suggested, and then McKennedy and O'Hagan, if I'm reading what they suggest correctly, here's the difference, and here's a step-by-step comparison. First line is identical, okay? Observations are the truth plus measurement error, and I'll take that as the conditional distribution of the data given the truth, okay? The second line then does not appear in what I was formulating. It's a little bit different. If you think of this as the following, if you let that second dot on the right-hand side be somehow meaningful as a probability statement, is that a statement that the truth is equal to something like a known offset, namely the model output, plus the discrepancy? Is that a conditional distribution for model output given the discrepancy? It's a little slippery, isn't it? I'm not sure. But again, if you do that substitution, then you get exactly what I described above. But you'll notice that I snuck something in, and that is I'm using a lowercase x on the right-hand side in the Kennedy-O'Hagan strategy. Because I think the right way to think about it is that that's no longer anything random. That's just a deterministic function of the unknown parameters, as opposed to the other side where I have x tilde equals x. I'm still thinking of x, the model output as random. I know it's not random, right? I know it's actually a deterministic output. This is a model for it that relates it to the truth. Okay, then on the left-hand side, we need a prior for the truth. We need a prior for the biases and a prior for the parameters. On the Kennedy-O'Hagan side, there's no truth left. Well, kind of a funny statement. But the analysis is now completed with a prior on the discrepancy and the parameters. And that means there's a posterior. They get a posterior that's a posterior on the discrepancy and the parameters, conditional on the data. There's no x in that line. There's no x tilde in that line. On the other hand, on the left-hand side, you'll see that there's a posterior on everything that was unknown, given the observations and also given the computer model output. But to get to that, I had to invent that funny second dot. Okay? Okay. I'll let that sink in. You can stare at that or decide if it's fair or whatever. But I think that's basically right. Okay. That's the end of this rather long introduction of what I wanted to show you. Now I want to turn to some real some examples. This first example is totally artificial. It's a simulation example. There's no real data here. But it's just a simulation to just look at the notion of putting error into a model. So this is actually a real domain in the Pacific. That box indicates the domain. Dots are, you can't see them probably, but dots are locations where there are data. And if you can see it, I hate to use this little guy because it's going to move the whole slide, but if you see. All right, I'm not going to do that. Sorry. You can see some lines at some angles, and that's where the observations are going to be simulated at. There was actually a real study here where there were some real observations, and that's where this comes from, but today's example is purely simulation. What we're going to do is imagine that the ocean is a two-dimensional surface. It has an X component and a Y component, okay? And we're going to study the behavior of a tracer as it moves across the surface of the ocean. That tracer, in this case, is going to be oxygen concentration. And we're going to write down a model for that true oxygen concentration. And this model is a differential equation in discrete time and space. Again, X and Y, lowercase x and lowercase y are spatial, and t again is time. So this says that the temporal evolution of the tracer is dictated by the quantities on the right-hand side. If you remember anything about some of these differential equations, take a look at that first term. It's the partial of an expression that looks like k times delta dx dx. Pardon the language. The symbols are meaningful. In a real advection diffusion equation, that k sub x would be a constant. It would come outside, and you'd have a constant times the second partial of the concentration in x. Similarly, the next term that constant would come outside, and you'd have a second order partial of x and y. The next two terms are advection. They're kind of saying how the oxygen is moving around in response to the way the ocean is moving around. So U and V there are ocean velocities in two dimensions. Think of a vector of ocean moving a little bit. U is a horizontal component, and V is a vertical component in that picture. And finally, the last term there represents a source or sink in oxygen. Okay, so this is almost an advection diffusion, except we're going to pay spatially varying diffusivities in here. The model is discretized on a total of 703 sites. Data are going to be simulated at 335 of those sites. And we're going to observe data for a year and try and reconstruct over that year, and then also predict out to 20 months. Is that all right? I don't know why I'm asking, because you're not going to respond. But again, we're going to think about the generated data. Y is equal to the truth at a certain location and a certain time, plus measurement error. And those are going to be simulated by actually running that model on the previous page and looking at the x's from it. Okay. Now here's the big idea. I don't know that diffusivities in the diffusion part of the model are actually spatially varying. As far as I know, an advection diffusion equation was a reasonable guess for this process. So now that's what you see in the X tilde model. You'll see that the constants have come outside, the advection part is the same, but now I'm going to say, well, I think it's actually an advection diffusion equation with the source of sink. But now here's eta. Eta is something, is this numerical model that I'm going to allow for. I'm going to model it, update that model, and bring it into this thing and see if I can recapture some of the real behavior of the real truth. As just a rough assessment of that model, we're going to look at average MSE. So X is the truth. Remember, we're just simulating one realization of the truth. We're going to simulate then X tilde and do a Bayes update on everything. The parameters are going to be treated as unknown constants. And I'm going to jump immediately to some results here. What you're looking at is that mean square error approximation, the difference between the model and the truth, where the model includes that model error. You see this is over 20 months, and what you see there are 4 curves. Those 4 curves correspond to what happens with different specifications of the model error. With me? Okay. So E1, the top curve, the worst curve there, is what if you use advection diffusion equation with no model error, But the truth was that crazy model I had on the first page of this. Well, you get an MSE that looks like that blue curve, and the scale here is not very important at the moment. I pointed to the screen. I always do that. Sorry. Excuse me. The next three then are different specifications, a priori specifications or models for how we think that model error might be. So the first one is that we think we're going to model a model error as a constant times first order different partials of x with respect to space. Cap A and cap B will be random variables that will be updated based on the data. The second one is to make those coefficients of those first order partials varying in time. Okay, so we might make them a linear function, a quadratic function with some parameters that vary in time and are updated. And finally, the fourth one there is to make those coefficients that go in front of x, of the partials, time series models. So we're going to think of the AT as being an AR1 model, the BT being another AR1 model. And we're just going to then fit this whole thing and see how we do. And how we do are the three curves, the three other curves in terms of mean square error. And the first thing to look at is, please note that we do a little bit better. Well, big deal. Well, the big deal is, please note that none of those correspond to the actual difference between the true model and the advection diffusion. Okay? They're all incorrect. The advection diffusion only screws around with this, and you can see how it affects it. It does make a little bit difference in the first, I don't know if that just covers in my screen or not, but it does change those derivatives a little bit, but it's not corresponding to any of the model errors that we specified in this example. Okay? So none of them are correct. But nevertheless, this is a little bit mystical, but I'm old enough I can be mystical. As long as the model error is flexible enough, the data can actually pull the model toward it, okay? Even if the model error specification that you use is not really the correct one. Okay. This is a graphic that shows what happens at the observation sites. If I average over all the sites, remember the observations, there's 300 and some out of the 700 or whatever. What's going to happen if I look at the mean square error over all sites? Well, it's not going to do as well, because at the observation locations, I should have the best chance of correcting the model a little bit. And that's what we see in this picture. Now the curve is relevant. If you look at the far left, the middle line there is labeled as 0.03, whatever that means. 0.03 was actually the maximum when we just looked at the observation sites. Okay? But 0.03 is not the maximum when we look at all other sites. Also notice there's a little separation among these things now. And also finally notice that E2 is actually starting to separate from the other two models. And I'll indicate why in a second. Here's it might look confusing, but here's another representation of that. What you're looking at is a representation or a presentation of the percentage of improvement using one of those three crazy incorrect model error specifications versus what happens if you just don't use no model error at all. Okay? And so now there's only three curves because I'm looking at 1 minus the ratio of mean square errors. Okay, and then I'm converting that to a percent. And now look at this. I think this is actually really startling. I get something like at least a 25% improvement, even averaging over all sites. I'm looking at the far left curve. Notice that that black curve is strictly above 25%. So I'm doing I'm typically doing a 25% improvement by putting in the wrong model error. It's a little bit right, but the wrong model error as opposed to no model error. My faith in statistics is restored in the sense that if you let the data speak in a flexible enough fashion, the data will help you. Okay. Some of you have seen this, and this has been around since 2008, but it's the most striking of real examples, and I apologize if you've seen this. I'm going to go through it really quickly, of actually putting in a model error into a model and getting something out of it that's useful. So what we're going to do, all that's irrelevant, what we're going to do is model the center of the glacier as it moves from the top, which is at the right-hand side, toward the sea, which is at the left-hand side of the picture. That red curve on the top are data that indicates the surface of the glacier. The blue curve on the bottom are data that indicate the bottom, or the ground that the glacier is moving over. Okay? And be careful about the scales here. The scale of the y-axis there is in meters, but the scale on the x-axis is in kilometers. So this is a run of 400 kilometers along the x-axis as this thing moves toward the sea. And notice that this thing is about 1 kilometer thick, roughly. Okay. Now, there's a whole bunch of approximate physics that go into stuff. There's a model for the surface of the thing. There's a model for the thickness of the thing. And there's a model for the velocity at the surface as the glacier's flowing toward the sea. That depends on some stuff. That model is extremely nonlinear, okay? That model depends upon a component that models the surface, the sliding at the bottom, and then a bunch of other stuff in terms of the derivative of the surface and the thickness or the weight of the glacier. Yada, yada, yada. It doesn't matter. Just think there's a model there, and it's very complicated and nonlinear. A component of that model is this thing, tau, okay? And that tau is well understood in the glaciology literature as an approximation, and they just say n plus some stuff. What we do is we put that stuff in and call it model error. Or in the paper, we call it a corrector process. I guess you could call it a discrepancy, we call it whatever. But I really like to think of it as a corrector process. Please note it's appearing in this model in a very, very complicated fashion. This tau, where it gets added, is actually then appears in the velocity model to a power, okay? That power is 3. But nevertheless, it's nonlinear and it gets very, very, very confusing. So the only thing I want you to look at and to remember is that we're putting in a model error deliberately, and then we're going to update that model error. Very non-informed prior, we say it's mean 0, and we didn't even put a spatial covariance on it. We just did something very, very, very naive. The bottom is our realizations up from the posterior. There's a big MC here. Realizations up from the posterior of that corrector process. And this is what I wanted to show you. Just putting in that corrector process and updating, you'll notice there's a light blue line. I hope you can see it. That's the 0 line. But you see some structure in the posterior. The posterior on this corrector process is positive for a while, then it runs down and goes negative. None of that was built into the prior, okay? That's the data speaking in a sense. And so it's correcting this thing to what it needs to do to match the velocity data and all the other data in a fashion that we find is useful. The most interesting thing about this is that in the paper we suggested that it has a physical interpretation. Places where we have to do this correction may actually be places where the glacier is either moving faster or slower than the naive physics suggests, and moving faster might be due to lubrication or melting at the bottom. Remember, this thing is a kilometer thick, so no one can actually look at what's going on at the bottom of this thing in terms of lubrication. But this would be a fantastic fact if this is ever confirmed as actually places where it's dry versus places where there's puddles of water. That's of interest, of course, because we expect to see more water as climate change continues. Okay, let me turn now to a bit about massive scales. And again, this is just a quick reminder. In terms of massive computer model output, where I can't actually run the model myself, we're going to look at a summary, and the true value of that summary is what I'm after and trying to understand. So we have observational data, same usual unbiased data observation model. And then the computer model has a similar model. I'm pretending it's observational data. I know it's not, but I'm acting as if it is, but I'm forcing a bias term, and a bias term that has to be modeled or dealt with, okay? I would never suggest anybody in the world try this without some kind of a bias term here, or a discrepancy, or a corrector, or a model error in the other setting. Okay. This is kind of fun. And it indicates what you can do a little bit if you like to. In this case, the true X that we were after and trying to understand is hemispheric monthly average surface temperatures. Okay, so XT there varies from month to month, and it's just bivariate. Okay, 2 dimensions from many tens of millions of dimensions down to 2. There's actually some observational data of perhaps suspicious quality, and assuming that observational data is unbiased is perhaps a leap. We also imagine that we have 2 climate models, big, gigantic climate models. Those abbreviations don't matter. This data came from NCAR. And here's what we're going to do. We're going to think of the climate model output, okay, as being equal to the truth, plus the next term is a bias that varies in time and depends on the model, okay? So one of these models these 2 models have different biases from each other. And then finally some ensemble variability as well at each time point. That's for that first model, PCN. That's a parallel climate model, because I have 4 ensemble members. There's no term there for the second one, because there's only one realization, or one ensemble member. But here's what I wanted to mention. There's a wonderful amount of physics that's going on into producing these models, but that doesn't exhaust climate scientists' understanding of hemispheric average temperature. And so I can actually have the opportunity to induce a prior process model, okay, extra prior information that is relevant, and still I get to use the climate system model information as well as this extra reduced thing. This could also be a simplified climate model if you like to, energy balance or something. But what we did is a very simple model here. And you can get to be really flexible in your statistics. You can make these parameters of this time series model depend on things like atmospheric CO2. I know atmospheric CO2 was prescribed in the other 2 models, but we can do it again. Why not? And the other thing that we allow is the parameters depend upon SOI, or Southern Oscillation Index. So we can bring El Nino into this, even though climate models are not very good at doing that. That's another argument for doing this kind of strategy. Okay, and then you have nothing comes for free, guys. I'm not trying to tell you that all this is easy, because you still have to model the biases, and you have to do so in a fashion that's not wacky. The way we did it is we had the models slowly vary, or the biases slowly vary in time. You can't let them jump every time without any information. You also can't leave them constant, okay? If you leave them constant, you'll underestimate your final uncertainty. That's subtle, but you can read about that in the paper. And there's some results. Okay, good. I forgot how long I'm supposed to talk. Peter, send something into the chat that tells me how long I'm supposed to talk, or just say it. But Peter probably is gone. Okay, anyway, I'm going to show you another example, and this one is kind of intense, and it's most of the publications here are not in the statistics literature, so that's why I'm going to show you this a little bit. It's an ocean modeling example. The ocean is actually the Mediterranean Sea. And what we're going to do is something similar. We're going to think about model output as if it's equal to the truth plus some bias plus some measurement error and see what we can do. In this particular case, we're just going to look at a specific location. We're going to look at vertical depth, okay? We're going to go down 300 meters into the sea and split that 300 meters into 16 vertical levels at average temperature at each of them. There's going to be two ocean models, number 1 and number 2, OPA and NEMO. The details are not critical for us. So those are big models that I'm not going to run, nor am I going to put model error into them directly, at least not today. This is kind of a fun example, and here's a separate ad independent of today's message. But I can't resist telling you this piece of the message. This is another way to think about Bayes or statistics support in the context of numerical modeling or very large-scale numerical modeling. What this problem does is it says, okay, we need boundary conditions to run the numerical model. Chief among them are winds, and if you followed some of our long-term contributions, we have a lot of models about dealing with Bayesian hierarchical models to reconstruct wind fields. We use Bayesian realizations from a posterior, winds, to drive those two ocean models. The stuff here that's in black, model 1 and model 2, are deterministic, gigantic models. But for each of the wind specifications, out comes an ensemble member of ocean, okay? And now what I'm about to show you is turning on Bayes again to post-process this data, okay? So we have Bayes at the beginning in terms of driving the model, and then we have Bayes at the end in terms of post-processing. And I think that's really kind of interesting, and it opens lots and lots of opportunities to do Bayesian things in gigantic model settings. These are, as I said, there's a sequence of papers about this in the Quarterly Journal of the Royal Meteorological Society, and you can see some of them if you choose. Okay, so all I'm talking about is the second part here, this investigation of the ensemble members after they've come out of the model. So again, I hope this notation is clear. I have computer model output. Symbol for that is always the tilde. I have some for OPA. I have some for NEMO. I'm assuming that they all have the same truth underlying them. Okay, nature is the same over this period of study. Each one has its own bias. OPA has a different bias than NEMO. And then I've added again those ensemble variabilities as well. I have model to model, realization to realization as the winds vary from different ensembles. That's what those extra variations are assuming. But I'm not assuming that the bias changes as I change the wind fields. Okay? As I said, nothing comes for free. We got to make a prior for X and a prior for beta. This seems a little wacky, but I actually think it's kind of useful. In this case, we actually make a prior based on somebody else's data analysis. So if you know numerical weather forecasting, you'll recognize those words. There's some data, actual observational data that was processed by another center. Didn't use OPA, didn't use NEMO, but it produced some analyzed fields. And what we're going to do is make our prior for X equal to the analyzed field. I would probably make our prior covariance, the analysis error covariance, if I had it. We did something wacky. And then again, we did the same thing with bias. You have to make the bias in there. You have to make it slowly varying in time, not too fast, not too slow. A little bit of art, a little bit of wackiness, and a lot of model building. If you have the opportunity, you do lots of model building on that thing, both to get a decent model and also to help people understand the biases or the errors that the model is making, so maybe they can help correct them. Okay. Last picture. So this is a wonderful picture because it didn't work. But it's not that Bayes didn't work, it's that the models are incredibly different. But Bayes recognizes that. So the column to the left are 3 realizations from one of the models. The center column is 3 realizations from another model. And the single thing there is the analyzed field for the same time period. And you'll notice that the difference between the 2 models looks pretty significant, and their difference from the analyzed field is also relatively significant. So this is kind of cool. You know, models are bad sometimes, or they have a lot of bias, and at least the Bayes is sensitive to that. So the top picture there is just the same picture that I had before. It was the prior mean, if you like. The picture on the left then is the posterior mean, and here's a big shocker. The 2 models didn't agree with each other. So what do you think the Bayes procedure is going to do? It's going to kind of go back to the prior because it doesn't like either of those models. That's because we didn't give the models any extra weight, okay? If you like one model versus the other, of course, you can affect that. Also, there's a lot of posterior standard deviation in these 2 things, and that posterior standard deviation kind of is a map of where all 3 of these data information sources differ. The interesting thing is again, you get an opportunity to inspect bias, and guess what? The top picture there on the left is the bias of one of the models. The bottom picture below it is the posterior and the posterior mean, if you like, on the other model, and guess what? They're exactly opposite. And that's because the top picture has to, whatever the bias has to do to get back to that prior mean. The other one is it has to do the opposite to get back to that prior mean. But what I like about this is it's hard to fool Bayes. You get to see this. You get relatively large posterior standard deviations, and I think the results are actually plausible. Of course, this is just one example. It would be nice to have another one where models actually agreed with each other a bit. Okay. I'm sorry if I went over, but thank you.
Thank you. You all have a clap button somewhere, so you can give a clap that way. So I can do it by proxy. Thank you very much. So just before we get to questions, and I'd written a bit about this before, we're going to try and do the questions through the chat window just because it's a bit easier. But I'm just going to go through a few logistic things before people start disappearing. And then after that, we'll get on to the questions. So I hope you don't mind, Mark. So, oh, it didn't come out quite the way. So the first thing is, since this is funded by the NSF, we'd like to keep track of attendance. So I can see how many people are there just as people who log in. But if there's more than one person logged in at a given location, please send me an email to let me know. The other thing I wanted to say was that seminar announcements are sent to node directors. So if you haven't got a seminar announcement, please talk to your node director to make sure that you're getting advertised. But you can also email me to get some information that way as well, and I'll add you to the list. The other thing I wanted to mention was our next seminar is already scheduled. So that's going to be Tales of Tail Dependence. Dan Cooley is going to give that talk on Wednesday, 9th of July, and he's going to be talking about extremes. The This is all organized by Statmos, so you can have a look at statmos.uw.edu. And remember, Statmos is a network, so the whole point of this project, this proposal, this grant, is to consider visiting someone in the network, and I like to explain it like this: statistics is more fun with friends. So these are all things to think about. Let me know if there were troubles. You can certainly send me emails about that. Okay, so let's get on to question time. So if you have questions, please write them in the box or send me an email, and we can pass them on. Okay, so the first one is from Whitney Huang. When adding things on the right-hand side of the equations, is it helpful in terms of if the terms are independent or at least uncorrelated? What have you been assuming about the joint distribution of your terms on the right-hand side of the models? So I think this went all the way back to the E as well, right at the start as well.
I'm trying to go back. Actually, it depends on where I am. In this context, in this example that we did, obviously the eta is not independent of much of anything, because please note that the eta actually is highly dependent upon x. So there's a very strong example of state-dependent noise. Okay. Jumping ahead to these, yes, we did assume that this eta was conditionally independent of everything else. Absolutely. So eta did not vary with thickness. Eta did not vary with anything else. Kind of like the discrepancy context in other settings. I'm worried about model error, but if I had a whole lot of prior information about it, I probably should be adjusting it and putting it into the model. So I have to walk this delicate line of using flexible class. I want to make something that's sensible, but I mean, I just kind of toss something in every once in a while because I don't have a lot of prior information about the discrepancy. It's kind of a tightrope, right? So if I had a lot of prior information, I would probably adjust and put that somewhere else in the model. Same thing here. Yes, the bias in these cases was again assumed to be conditionally, x and the bias were assumed to be independent. In these lower dimensional settings, it is possible to make the bias have a distribution that relates to the truth. For example, sometimes we know that a particular model might not put enough moisture into something, okay? So when something is supposed to be, when x is kind of representing something that's really moist, maybe I know that there's a negative bias in x tilde. That could certainly be done, especially in low dimensions, and I urge people to do it. In fact, there's a lot of other stuff you can do here. There's no reason you can't make a nice big linear model or generalized linear model. In fact, to incorporate lots and lots of other stuff. That's one of the positive things about going to this lower dimension. As long as that lower dimension is still valuable, you can do a lot of things with it, and that's useful. Is that okay? Did I answer enough of that, Peter, you think?
I think so. Jennifer Honing asks, how do you deal with non-identifiability between terms in the bias and the error?
Good question. Depends on where it is. In some sense, even here, there's a non-identifiability issue that's only broken because of the prior. In these contexts where I have very little information, identifiability can be a problem. And here's the knee-jerk response to get out of this, and that is, as long as I use proper priors, the posterior exists. As long as I'm careful and make inferences about identifiable functions, I'm okay. If I make inferences about non-identifiable things, then I have to remember that my prior is actually controlling a lot of that inference. The other warning about doing that is it can sometimes be a problem numerically. It can slow down your MC to be trying to analyze and update something where there's a whole collection of values of things that give you very similar likelihoods. But yes, it's a problem. I don't have a pat answer. Case by case is definitely something, and absolutely you're right that you have to watch out for it. We've never found it to be a serious problem. We've actually done some bigger examples where there's very strong non-identifiability among some things, but as long as we remember not to make strong inferences about them, we're okay. I don't like to just change the model so there's not identifiability is not a problem, because it seems to me that that's actually integrating out things without using the data. Little probability.
Is someone else asking?
Mike? Just type it.
Yeah. Oh, 2 questions. So do you have recommendations for determining the prior for X for applications with relatively little data? Yeah,
call an expert. I know that sounds kind of silly, but I think that's something that we underestimate. You're thinking about this dimension reduced case, I think. In the massive case, then that's more the ADA problem that is different. But in this context, you know, I don't think I have a pat answer that I wouldn't say is true for any complicated statistics model. Try and get something flexible, try and extract as much data, try and get something relevant, and try and talk to people who know more than you.
That's good. Ralph?
Ralph is typing. Hey, Ralph. Those of you who don't know, Ralph is an honorary Bayesian statistician. Ralph is a longtime collaborator and does a lot of the answers a lot of the questions of the previous that Mike G asked. Go talk to an expert, and Ralph is often ours.
Okay, Ralph has written, identifiability can be skirted a little by using the model output with a tight prior for fields that it does well. If we use the physics part of a coupled ocean ecosystem model to gain some insight into non-identifiable eco stuff.
I agree, Ralph. That's absolutely correct. Again, the issue is, you're absolutely right, and that's a great example of having proper priors, and it's the priors that break non-identifiability issues a lot. And when Ralph is doing it in this context especially, it's very, very useful and plausible. Thanks, Ralph. Good example.
Any other questions? Oh, Ralph is writing some more. Thanks all. Okay, I wanted to ask just a quick question, because there was a bit at the start that said dimension reduction bridges scales. And I was wondering, how did that compare to upscaling and downscaling approaches that people use?
My student Yenny and I just had Yenny had a paper that I helped a little bit on that just came out in JASA. That is an upscaling and downscaling downscaling a large model output to another large scale model. And what we did is we did EOFs sort of in both cases. Did EOFs for the guy who was the target of our inference, and then found the best vectors and coefficients that we could predict the EOF coefficients the best on. That's an example of what I meant. So I do a dimension reduction, and then I operate on the dimension reduction controls, such as the coefficients, the amplitudes, as if they're my process. And now I get to do as much flexibility and fun as I can possibly do. Another example is this SST model that some of you may have seen that, let's see, Noel Cressy and Chris Weichel and I played with, in which we have very large space-time fields, but we end up actually not predicting the fields directly, but rather the coefficients of EOFs from those fields. I'm using EOFs if you're not familiar with principal components. So there's another way to think about it. I had other things in mind, but they would take a lot more time, and there's something I'm working on right now. I guess I shouldn't say that. I shouldn't have put that on the slide when I'm not willing to say everything I want to do. Oh, I'll say it. Linking emulators is another way to think about a dimension reduction. And that's there you go.
Great. Wonderful. Any other questions? Okay, well, I'd like to take the chance to thank Mark again for giving this wonderful, interesting talk. And I'd encourage you, fresh after the July 4th weekend, to come back and join us for Dan Cooley's seminar. So thanks a lot.
Thanks, everyone.